Hello, and welcome to your stats cooldown here. All right, so what do we got going on? In the game of Scrabble, each player begins by drawing 7 tiles from a bag containing 100 tiles. There are 42 vowels, 56 consonants, and 2 blank tiles. You choose 7 tiles and are surprised to discover all of them are vowels. We can use a simulation to see if this result is likely to happen by chance. So state the question of interest that we are investigating. Basically something along the lines of, what is the probability of drawing 7 vowel tiles from a standard Scrabble bag? And again, this is one that we could calculate this out by hand. All right, this one is not overly complicated. It'd be 42 over 100 times 41 over 99 times 40 over 98 times 39 over 97 times 38 over 96 times 37 over 95 times 36 over 94. All right. But again, simulation is a way to do this. All right. And we can trust that over a large enough trials, it's going to approach this answer anyways. So how would you use random digits to imitate one repetition of the process? What variable would you measure? All right, so how could we use random digits in a case like this? We could say, all right, numbers 1 through 42 represent vowels. 43 through 98 are consonants. And 99 through 100 are the blank tiles. Okay. So what we could do is we could generate 7 unique random numbers, one to 100, and count the number of values between 1 and 42. All right, and that would be a way of simulating this. And we could have that happen on a computer or a calculator and then run it, thousands or hundreds of thousands of times to arrive at the actual probability that this would be simulating. In 1,000 repetitions of the process, there were 2 times when all 7 tiles were vowels. What conclusion would you draw? All right, so basically this is your experimental probability. So your experimental probability is 2 over 1,000, which works out to be 0.002. All right, or another way you could write that is 0.2%. So not even a full percent, but 0.2%. So basically, it is very unlikely to draw all vowels, but not impossible. All right, so if it happens, it's pretty crazy that it happened because there was only a 0.2% chance of it happening, but it's possible. Right? There's no reason it can't happen. Right? But again, this idea of creating a simulation using random numbers to simulate some sort of real world scenario. There are many games that use dice other than traditional six-sided die. One popular die is the four-sided die. List a sample space for rolling a four-sided die twice. So again, just this idea of saying, okay, if each die has four sides and I'm rolling it twice, I should have 16 total options. And then just making sure that you do it in a systematic way so that you don't miss one of those options. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, and then 4, 1, 4, 2, 4, 3, 4, 4. All right. What is the assignment of probabilities to the outcomes in the sample space you created above? Well, assuming it's a fair die, and we have no reason to think that it's not, it would just be 1 over 16. All right, each of those is equally likely. Each outcome is equally likely. What is the probability that you will get a sum of 5 when rolling those two dice? What is the probability that you will get a sum other than 5? All right, so probability of getting a 5, we can say, all right, well, there's one way we can do it. There's another way we can do it. There's another way we can do it. There's another way we can do it. So the probability of getting a sum of 5 is going to be 4 out of 16 or 1 out of 4. All right. The probability of getting a sum that's not 5 is just the complement. All right. So we automatically know that that's 12 out of 16 or 3 out of 4. All right. These two are connected there because they're summing to 1. So they're complements of one another. All right, let's take a look at the back here. In each of the following situations, that should say state, not stat, whether or not the given assignment of probabilities to individual outcomes is legitimate, that is, satisfies the rules of probability. If not, give specific reasons for your answer. All right, so the key to this question is it's saying satisfies the rules of probability. So forget what you know about decks of cards or dice, and instead evaluate it as, does it satisfy the rules of probability? All right. So in this case, if we're looking at this scenario, you might be saying to yourself, well, the probability of rolling a 1 isn't going to be 0. The probability of 6 isn't going to be 0. Well, it could be. It could be a weird die that doesn't have a 1 or a 6. What's going on here, and the part that's more problematic, is that 1/6 plus 1/3 plus 1/6 plus 1/6 equals 5/6. So this can't be a probability model because it doesn't sum to 1. All right, so again, if this had said P of 6 is 1/3, then this, I mean, not 1/3, 1/6, then it could have been a valid model, all right, as long as they had summed to 1. And maybe this is just a weird die that has 2 3s and no 1s. So it's impossible to get a 1, but it's a little more likely to get a 3. That's possible, but this is not possible because there's a 6th that we're missing somewhere. All right. Your probability model should account for all possibilities, which means across every possibility, it needs to sum to 1. And if it doesn't sum to 1, it's not a valid model. So this one, we've got a different situation. All right. This is saying choose a college student at random and record their gender and enrollment status. So basically the way they're breaking this down is you're either full-time, part-time, and you're either male or female, but altogether, those should sum to 1. So here we've got 5, 6 plus 0.44 plus 0.24 plus 0.17, and that's going to work out to be 1.41, which is also invalid, all right? Probability models should not sum to more than 1. And you might be saying to yourself, well, wait, is there overlap? No, there's not overlap. You're either, each one of these groups is its own thing. Female full-time, female part-time, male full-time, male part-time. Those are distinct groups. So we should be able to add those up. There should be no double counting, and they're not summing to 1. All right, last but not least here, we've got deal a card from a shuffled deck. So we've got 12 clubs, 12 diamonds, 12 hearts, and 16 spades. All right, that sums to 52. All right, and if all of those are over 52, it sums to 52 over 52, which is 1. All right, so it might not be a traditional deck of cards, but it's a valid model. So not a normal deck of cards, but a valid probability model. All right, and just keeping those two things straight. 6, Canada has 2 official languages, English and French. Choose a random Canadian and ask, what is your mother tongue? Here's a distribution of results. English, French, Asian Pacific, and then other. What probability should replace the question marks for other? Again, this is just relying on that fact that models always sum to 1. So it would be 1 minus 6.3 minus 0.22 minus 0.06. So those are going to sum to 85, 91. So that's going to leave 0.09 left over. All right. So again, the model has to sum to 1. So we can use that to figure out the missing piece there. And then what is the probability that a person's native tongue is not English? What is the probability that a person's native tongue is a language other than English or French? All right, so we know the probability of English is 0.63. So the probability of not English is 1 minus 0.63, or in this case, 0.37. All right, and you could also get that by just saying, okay, well, it's 0.22 plus 0.06 plus 0.09. Either way will get you there. And you're going to see that a lot in this unit. There's usually more than one way at arriving at your answer. Whichever way makes the most sense for you is the one that you should do. And then it says, what is the probability that a person's native language is a language other than English or French? So again, 2 different ways to do this. You could just say, okay, the probability of English or French is 0.63 plus 0.22, which is 0.85. So the probability of not English or French is 1 minus 0.85, which equals 0.15, which again, you could have just gotten by doing the 0.06 plus the 0.09. All right, so either way you do it is fine, doesn't really matter. You're going to get to the same place anyways. But again, taking advantage of the fact that a probability model is always going to sum to 1. All right, That's it for this. Hope it was helpful. Have a great day, and I will see you when I see you.